Hello everybody, welcome to the second video on section 7.2, our first day of the crash course in linear algebra continued. So what did we do in the previous video? We answered these 5 questions here, although I guess I myself only answered 4 of them. I punted off to a different video for matrix multiplication. In this video we will quickly answer these last 2 questions. These are more calculus-y questions, right? Derivatives of matrices, and then using linear algebra notation to help us reconceptualize a system of differential equations. So question 6, how do you take a derivative of a matrix? So suppose your matrix is this A right here. If we were in class, right, I would stare at you and ask you to take a guess. What's the derivative of that matrix, I would ask. And then there'd be silence, and then somebody eventually would guess this. You would say, well, I don't know, man. Like, I would just take the derivative of every individual thing I see. The derivative of e to the t is e to the t. T squared minus 3t, 2t minus 3, and so on. And that's indeed like exactly what you do. Okay, just to take a derivative of a matrix means to just individually differentiate each entry. So derivatives with matrices works exactly the way you think it should. Okay, so last question of the section. Why bother with this, right? How does linear algebra notation help us think about systems of differential equations? So first, just a little bit of preliminary notation. A bold X for us will always denote this vector, x1, x2. And if the system we're thinking about had a third variable, x3, there'd be like an x3 down here. If there were a fourth variable, x4, it'd be down here. So a bold X is just x1, x2, x3, and so on all the way down, however many variables you are thinking about. So bold X depends on the context is all I'm saying. Okay, so once you have bold X up and running, bold X prime is just put primes everywhere, right? Differentiate the individual entries. Again, it's worth mentioning here, x1, x2, x1 prime, x2 prime, these are all functions of time. I'm suppressing that of t notation just to streamline the way it looks, but they are all depending on time. So here is a system of differential equations from previous videos from section 7.1. I claim this system of 2 equations can be written as a single equation using matrices like this. Bold x prime equals, notice there's a coefficient matrix here, a 1, a 1, a 4, a 1, times bold X. Okay, so I claim that this guy here can be sort of more compactly written like this. So why would that be the case? Here's this matrix equation I just presented. Let's think about what it's saying. What would it mean for this equation to be true? Okay, well, bold X prime is x1 prime, x2 prime, that vector. Bold X is x1, x2. What if I multiplied the right-hand side here? I have a 2 by 2 matrix times a 2 by 1 matrix. What if I did the matrix multiplication? What would that look like? I would do a 1 times next 1 plus a 1 times next 2. Again, I'm assuming that you understood that matrix multiplication video. That'd be the top entry here. And then I would have 4 times x1 plus 1 times x2 to give me my bottom entry here. And now I have matrix equals matrix, so the top entry here has to equal the top entry there. The bottom entry there has to equal the bottom entry there. And you recover those 2 original DEs that I started with, right? x1 prime is x1 plus x2, and similarly x2 prime. Okay, so this matrix equation here is just sort of a more compact way of writing the original system of DEs. So the punchline here is that a linear system of DEs can be written using matrices, sort of as a single matrix equation. So I want you to do the same thing here. Write this system of DEs as a single matrix equation. So pause, see if you can mimic what I did on the previous slide. Okay, so assuming you're back, there's the answer. As with the previous slide, you just sort of pluck off the coefficients. You're separating coefficient data from the variable data, like on the previous slide. Here's another one, a little trickier, but see if you can write this system of DEs as a single matrix equation. So pause the video and see if you can do that. All right, assuming you're back, let me just show you the answer. So there's a bunch of x1 and x2 stuff, right? Then you got this free floating t stuff, but you can just write that free floating t stuff as like a free floating t vector. And notice there's no x2 in the second equation, so that's why there's a 0 there. So let's just unpack this for a second. Let's rewrite this. Let's see what's actually happening here. So bold x prime is an x1 prime, x2 prime. I did the multiplication, sorry, I can't get the highlights to work, right here. So I have a 6x1 plus x2, top entry. 12x1 plus 0x2, bottom entry, 12x1, right? Plus, in the top, x1 prime is supposed to have a plus t squared. In the bottom, plus an e to the t. So if I take this guy and combine everything, the t squared goes up top, e to the t goes to the bottom, and then what am I saying? I'm saying x1 prime equals 6x1 plus x2 plus t squared. That's precisely what was said right there. Similarly for x2. Okay, so all that said, you can take a system of DEs, a linear system, and rewrite it as a single matrix equation. What's the point of that? Okay, what is the point of starting with this? Sorry, these two guys here, and rewriting them like this? Why bother doing that? Okay, why bother rewriting a system of DEs using matrices? The answer is that it allows us to take a calculus problem and reconceptualize it a bit more as a linear algebra problem. And the thing about linear algebra, I mean, you guys don't know this because you haven't had the course, but it's like this vast field. It's like this gigantic field of math that for us is just going to act like this gigantic tool that we can reach out and grab. So the field of linear algebra is just like a big old hammer. And we're going to use that hammer to just smash these systems of DEs and get from them what we want, which are solutions. So rewriting systems of DEs as matrix equations, so thinking of them more in linear algebra language, allows us to use this linear algebra tool. That's the basic answer for that. So again, it doesn't seem like we're doing anything, really. So if you think about it, right, why does it matter if I think of these two equations separately, or I pluck off the coefficients and think of there being a matrix there? It doesn't seem like it makes a difference, but it actually does. It actually makes a large difference. It lets us use linear algebra tools on this matrix to tell us what the solution is. Okay, so we still have one section to go after this. We still have section 7.3 about just raw linear algebra. Okay, so we're not solving the systems here, right? We're not doing anything calculus-y here. After section 7.3, though, we will see why going from these two lines to this one line is actually pretty useful. So we'll pick back up after 7.3. We will skip 7.4. We will pick back up in 7.5 and actually solve systems of DEs. We will think of the systems like this and use linear algebra to solve this.